Hi all, let's take a look at your practice for your second test covering sections 2.8 through 3.6. Just like on our first test, please do remember that problem by problem, your test will be extremely similar to this. So exact same concepts on each problem, even though no problem will be exactly replicated. On this one, since I'm starting at section 2.8, the first problem should be no surprise that it's an intermediate value theorem problem. And I'm asking you to use the intermediate value theorem to show that x cubed plus 7x is equal to 35. So what the intermediate value theorem is going to enable us to do, if we know that a function is continuous, and of course we know all polynomial functions are continuous, then all that we have to do is evaluate it at an x value that is less than 35, and then evaluate it at an x value that is greater than 35, then you're guaranteed that there is an x value in between the two that you found where the y value will be precisely 35. So that's what I did on this problem. I said, okay, intermediate value theorem is going to require me to let f of x equal my function. Now, I want to evaluate that function at a value that's going to give me a y value less than 35. So you'll see I evaluated it at 2. And I said, well, f of 2 then is going to be 2 cubed plus 7 times 2. That's 8 plus 14 for 22. Okay, have a y value lower than 35. Now I needed to input an x value that gave me a y value greater than 35. Well, notice all I have to do is go right up to 3. F of 3 would be 3 cubed plus 7 times 3. And then I can say, well, that's going to be 3 cubed is 27 plus 7 times 3 is 21. 21 plus 27, 49. Okay, now I know that since f of x is a continuous function, and since f of 2 gave me a y value lower than 35, and f of 3 gave me a y value greater than 35, there exists an x equals c. That's the value of x that we call a success. We say, oh, if it's a success, it's the value x equals c. And this stands for belonging to the set of numbers. And it's belonging to the set of numbers between x equals 2 and x equals 3. The value of x that's a success is c, and it's belonging to the set of values between 2 and 3. And we know that at that value, f of c will be 35. So this is, and you don't have to word it exactly like I'm wording it, but this is the way that the intermediate value theorem really should be worded. You say, since f of x is continuous, and f of 2 is 22, and f of 3 is 49, there exists an x equals c belonging to the set of numbers between 2 and 3, where f of c is equal to 35. Quod erat demonstratum. Now, for our next problem, it may be the longest problem on the test. I'm asking you to find the first 4 derivatives of the square root of x to the 7th minus 5 on the 7th root of x to the 6th minus 7x squared. Okay, so you'll see, of course, I went ahead and wrote down the problem here. This is my function. The first step, crucial. I need you to be able to write those radical expressions correctly as fractional exponents. The square root of x to the 7th means x to the 7 over 2 power. Remember, when there's no index on a root, it's understood to be the second root or the square root. This next one is going to be minus 5x to the 6/7 power. It's always power divided by the index. And then, of course, minus 7x squared. No big deal with that one. Okay, now, in taking the derivative, first thing I do is I take the derivative term by term. Derivative of x to the 7 over 2 is 7 over 2, x to the 5 over 2. I had to subtract 1 from that exponent. Now the next one, I'm bringing down 6 over 7 times negative 5. That's going to give me negative 30 over 7. And then I'll have x to the 6 over 7 minus 1 power. That's where I'm getting the negative 1/7 power. 6 over 7 minus 7 over 7 is negative 1 over 7 there. And then, of course, the derivative of 7x squared. 2 times 7 is 14, x to the 1st. Now, I've taken the derivative correctly here. Since the original is written in radical form, each of my answers should be in radical form. So when I rewrite 7 over 2 x to the 5 over 2, I need to understand that that x belongs in the numerator with the 7 and say that that is x on the square root of, that is 7 on the square root of x to the 5th power all over 2. And then since this x is to a negative exponent, it belongs in the denominator with the 7. So I can say, well, that's just going to be minus 30 over 7 on the 7th root of x to the 1st power in the denominator. That's where that came from. And then minus 14x, you don't need to rewrite. For the second derivative, I'd much rather look at the fractional exponents when I use the power rule. So I'll say, okay, the first one, you're going to have 5 over 2 times 7 over 2 for 35 over 4, x to the 5 over 2 minus 1 power. Well, 5 over 2 minus 1 is 3 over 2. Then I go to the next term here, and this coefficient comes from, I need to multiply 30 over 7 times 1 over 7. I also know a negative times a negative is going to be a positive. I'll get positive 30 over 49 there, and I'll have x to the negative 8/7 power. And then minus the derivative of the last term there, you'll see the minus 14. Now, when I put that in radical form, your first term, 35 on the square root of x cubed over 4. Second term, you'll have plus 30 over 49, and down in the denominator with the 49, you'll have the 7th root of x to the 8th power down there, since again, it's to the negative exponent, and minus your 14 on the end. For the third derivative, we just keep on this glorious process, and you'll say, okay, first term, 35 over 4 times 3 over 2. 3 times 35 is 105, 2 times 4 is 8. So my coefficient is 105 over 8. And then the x is going to go from the 3 over 2 power minus 1 to get to the 1/2 power. The next term, I know a negative times a positive is going to make this term negative, so I subtract the second term, and I'll have 8 times 30 is 240. 7 times 49 is 343. So I just get minus 240 over 343. X to the negative 8 over 7 minus 7 over 7 power. That's where the negative 15 over 7 power comes from. And then notice here, third term canceled out because you said, well, derivative of any constant is 0. So that last term, no derivative, there's no need to put a plus 0 there. So now just rewriting this first term is going to be 105 on the square root of x to the 1st over 8. Second term, minus 240 over 343 on the 7th root of x to the 15th, all down there. And again, remember, that's in the denominator because the x had a negative exponent. Between this step and the next step, the first term of x is also going to move down to the denominator. Right now, it's still in the numerator because it's the positive 1/2 power. But when I take the fourth derivative, that 1/2 is going to come down in front, multiply the 105 over 8 to give me 105 over 16. Then I'll have x to the negative 1/2 power. Then I can say, okay, first term's done. Second term, you'll have a negative times a negative is a positive. 240 times 15 is 3,600. 343 times 7 is 2,401. So I get the coefficient out front, and that coefficient doesn't reduce, so I'll just leave it like that. The exponent becomes negative 15 over 7 minus 7 over 7. That's negative 22 over 7 power. So then I say I want this final answer put in radical form. For the first time, our first term also has the x in the denominator because it's the x to the negative 1/2 power. So that means the square root of x to the 1st power in the denominator. It'll be multiplying the 16 down there. And of course, 105 in the numerator. Second term, no surprise, you'll have the 3,600 over 2,401 on the 7th root of x to the 22nd power. Final answer there. It's a beautiful problem. For the next one here, we have our physics application problem. It says you have a rock that's being blasted vertically upward with a velocity of 400 feet per second. It's going to reaches a height of, I give you a position function. Position at time t is 400t minus 16t squared after t seconds. And I say you must show calculus in solutions. I know some of you are in the applied classes where you memorize the formulas and stuff. I need to see the derivative taken specifically for the velocity function here. So when I ask you how high does the rock go, you say, well, the logic I need for that is all the way up, that rock is going to have positive velocity. When it reaches its maximum height, the velocity is going to be 0. And then all the way down, it's going to have a negative velocity. So I just say, well, all I need to do is find the velocity function, set it equal to 0, and that's going to give me the time at which it reaches maximum height. Then all I have to do is plug that time that it reaches maximum height into the position function to find out how high it goes. Okay, so if I'm thinking about that, I can say, well, here's my position function. And like I was saying, we need to find the velocity. Well, velocity is the first derivative of position since it's the change in position over the change in time. And so my velocity equation here, just the derivative with respect to t of 400t is 400. The derivative with respect to t of minus 16t squared becomes minus 32t. So I have my velocity function here. Now, the maximum height is going to occur when that velocity function is set equal to 0. So when I did that, I was just thinking, well, it'd be when 400 is equal to 32t, which means t has to equal 400 divided by, oh, and that's a 32 there. That's a, I started to call it a typo, but it's a mistake. That's a 32 there, but my answer is correct. I just, for some reason, put a 12 down there. So 400 over 32, that is 12.5 seconds. I bet I was going ahead and getting the answer 12.5 seconds and I accidentally put the 12 down there. Please don't be thrown off by that. Now, in the next part of this problem, we're asked to find the maximum height. All I know now is that the maximum height occurs at 12.5 seconds. Well, I need to plug that 12.5 seconds into my position function. And when I do that, I'll get the 400 times 12.5 minus 16 times 12.5 squared, and I get 2,500 feet. Okay, so now, just from knowing that, I went ahead and drew my little graph here. I know at time 0, the position is going to be at 0, and then it's going to go up at 12.5 seconds. It's going to reach its maximum height at 2,500 feet, and then it's going to come back down. Probably, and well, in fact, it is exactly another 12.5 seconds for it to hit the ground. Now, I'm looking for the points at which the height is 2016 in part B of this problem. So I've already done part A. Part B is asking how fast is the rock traveling when it's 2016 feet above the ground on the way up and then on the way down. So what I did in order to find this out, I'm going to have to plug some times into velocity functions. But I first need to find out how to get to those times. So I would strongly recommend just use your calculator to help you. Quadratic formula would be another option, but calculator is what I would say is the option of choice here. Notice I'll just put in 400x and then minus 16x squared. So I'll put the position function in y1. We need to know when is the position 2016 feet. Now, I already know a great graphing screen because x is representing time in this problem. So it doesn't make sense for x to be a negative value. So I'll start x at 0. Now 10 is not enough because we already know the maximum height occurs at 12.5 seconds. So if you want to follow the entire path, it takes 12.5 seconds for it to go up. It's going to take 12.5 seconds for it to go down. So I would recommend just choosing 25. I double the time it takes for it to get to maximum height. And then you can say, well, what about the y values? The highest y value in our problem is 2,500. I want to go up above that just to make sure I include it in the screen and it's not at the very tip top of the calculator screen. So I'll go 2,800. And I'm starting at negative 300 just so it shows the x-axis in there nicely. So I want to go a little bit below the x-axis, a little bit above the maximum to set up the y value range. Now notice this should make a beautiful graph. Yeah. Okay. So here's my graph now. And I'm looking at this and saying, well, all right, if I hit trace here, yep, I'm getting that the maximum value is at 12.5 seconds and it's at 2,500 feet. But now the question is, when is it at this height of 2,016 feet? That's why I put that in as Y2. That's what I needed to find. All you have to do to find that is go second calc number 5. We're finding an intersection. Second calc intersect, hit enter 3 times, first curve, second curve, guess, enter, enter, enter. And you'll see I get my first answer of 7. Now, I already know what the other answer is just by logic, because whenever you think about it, you say, okay, so the time from this position to the maximum position was 7 to 12.5 seconds. Well, 12.5 minus 7, that's 5.5 seconds. It took 5.5 seconds to get from this height to the maximum height. Well, I guarantee you it's going to take 5.5 seconds to get from the maximum height back down to that same height in this direction, because the only force slowing it down on the way up is gravity. The only force speeding it up on the way down is gravity. So I can say, well, okay, then this has to be 12.5 plus 5, which will give you 18. Now, if you just want the calculator to determine it, you can go second calc 5 again. But unlike the first time, you don't just randomly hit enter, enter. Well, you do hit enter twice. But the third time, if you hit enter 3 times, you're going to get the exact same answer you already got. You're like, well, congrats, you just got the same answer. Not good. Second calc 5, hit enter twice. The third time, when it says guess, just arrow over closer to your other point, and that will be fine. As long as the cursor is closer to that point than your original, it will guess that point, and it tells you that you have the intersection at 18, 2016. Now, the answer to the question here is we need to know the velocity of the rock when it's 2016 feet above the ground on the way up and on the way down. What I'm wanting you to think of here is that the velocity absolutely must be equal and opposite. If it's not equal and opposite, then I've done something wrong. But please do notice, if you plug 7 into your velocity function, you'd have 400 minus 32 times 7. That's going to give you 176 feet per second. Please do put units. If you plug 18 into your velocity function, 400 minus 32 times 18, you're going to get a negative 176 feet per second. Exactly what we should expect, and that's confirmation that the problem is done correct. At any height, the velocity is going to be the same on the way up as it is on the way down. Now, number 4, when we look at that, this is a problem where I'm wanting you to understand the connection between the graph of a function and its derivative. So implicit in this problem is that you understand when an original function is increasing, its derivative is positive. When an original function has a maximum or minimum value, it flattens off, and thus its derivative is 0. When an original function is decreasing, its derivative is negative. Okay, so now I'll give you the graph of a derivative. So please notice I say use the following graph of f prime of x. So on the practice test and on the test, I will give you a graph of the derivative of f of x. From the graph of that derivative, you're supposed to determine things about the original function. So on what intervals is f increasing? So please don't look at this and say, oh, this is increasing from 0 to infinity. That's terrible. I don't want to know when the derivative is increasing. I want to know when the original function is increasing. So you say, oh, well, the original function is increasing whenever the derivative is positive. When is this derivative going to be positive? from negative infinity up until the ordered pair -3, 0 here. And then again, this ordered pair labeled as 4, 0. So you'd say, well, it's going to be positive from negative infinity to -3, union 4 to infinity. That's when it's going to be increasing. Well, when is it going to be decreasing? It's decreasing whenever the derivative is negative. When is this derivative going to be negative? Well, between these two ordered pairs of the intersections. So it's going to be negative from x equals -3 till x equals 4. So the original function is decreasing between -3 and 4. So now please notice that's precisely how I had this labeled out. It's increasing whenever the derivative is positive. It's decreasing whenever the derivative is negative. Now, it might help to go ahead and do part C before doing part B. So when I'm thinking about how would I do part C, okay, here's my derivative. I'm saying this is the original function. So when I see this derivative, all I know is that, well, I need to draw a function that is forever has a positive slope until it gets to x equals -3. That's precisely what I did. I said, I have a function that is increasing until x gets to -3. The derivative becomes 0, so the original function flattens out. Then the derivative turns negative in between x equals -3 and +4. Well, what does that mean? It means the original function decreases, has a negative slope in between -3 and 4. Since 4 is an x-intercept, that tells me that the derivative is 0, which means, okay, the slope of your original function is 0 when x is -4, so it stopped decreasing. And then what happens after 4? Well, your derivative turns positive, so your original function turns increasing. And then from that, I can easily answer part B and say, well, since my function was increasing before -3, decreasing after -3, -3 had to be the location of a maximum. Since my function was decreasing before x equals 4 and increasing after it, it had to be the location of a minimum. And that's what I'm wanting for number 4. I want you to connect the graph of a derivative with what the original function is. Now, please do remember, when I ask you to sketch a possible graph of f, all you're going to know is the approximate shape of the function. I know it's going to look something like that. What I don't know is the y values. That's why you won't see me label any y values here. This could be shifted way up, it could be shifted way down, but the general shape has to look like this. It's going to increase to -3, it's going to decrease between -3 and 4, and it's going to increase after 4. That's what the graph of that derivative tells me. Okay, now up for the algebraic limit definition of a derivative problems. This would be like section 3.1, where we were supposed to work the problems algebraically. And we have 2 limit definitions of the derivative that can do that. I strongly recommend the limit as h approaches 0 for any polynomial where you're going to have to find the derivative algebraically. And then anytime it's not a polynomial, I recommend the limit as x approaches a. You'll see that's what I did in my solutions. When I look at number 5, I have, okay, I'm supposed to find f prime of a if f of x is 5x squared minus x. So you'll see I'm just using the limit definition right here. The f prime of a is going to equal the limit as h approaches 0 of f of a plus h minus f of a over h. And then when I apply this formula to this problem, f of a plus h, all that's telling me to do is wherever I see an x and f of x, replace it with an a plus h. So f of a plus h is 5 times a plus h quantity squared minus a plus h. So all of this, I always group f of a plus h with a bracket. All of that is f of a plus h. Now, we're subtracting f of a from that. Well, f of a is just my function evaluated at a. So instead of 5x squared minus x, it's 5a squared minus a. Now, I know that the terms of f of a and f of a plus h always cancel. Before I can cancel any, though, I need to go ahead and do the algebra on that first group. A plus h squared, please remember, is a to the second plus 2ah plus h to the second. It's not just the square of the first term and the square of the second term. That's a bad algebra mistake I see made way too often. So if you need to FOIL out a plus h times a plus h on the side to get a squared plus 2ah plus h squared, please do that. So that's what I did. I just said, well, I know that this is a trinomial, a to the second plus 2ah plus h squared. I need to multiply that by 5. So you see I get a 5a squared plus 5 times 2ah gives me 10ah plus the 5h squared. So I distributed that through this group. Then I have minus a minus h. All of this is my f of a plus h, and I still have to keep it inside of a limit as h approaches 0. That limit must be there until you can finally allow h to become 0. So I have a factor of h in the denominator. It can't be 0 right now. I go ahead and I subtract the f of a in this step. And please notice, just like I said, the terms will cancel. You'd have a 5a squared minus 5a squared cancels. Negative a minus negative a goes away. And so what I'm wanting you to remember after that, yes, the terms of f of a and f of a plus h always cancel. Any term that doesn't cancel, I promise you, always has a common factor of h. I was so confident that I would have a factor of h left that in the next step, and again, I still have to put my limit as h approaches 0, I went ahead and factored in h out. I knew they had to have a factor of h. Okay, 5a squared canceled. My first term that didn't cancel was the 10ah. Factor an h out of that, you have 10a. My next term, 5h squared. Factor an h out, you'll have plus 5h. Now, please be careful with the next term. This minus h did not cancel. The minus a did, of course. This minus h did not cancel, but you factor an h out of it. H divided by h still leaves you a minus 1 that must be put. A lot of students will make the mistake and say, oh, h over h cancels, and so you don't need it. Oh, you need it. H over h is 1, must have it because it's being subtracted. Okay, so now I have my h times this group all over h. This is the point in the problem where you can eliminate h. You can say, well, I have a factor of h in the numerator and denominator that can and should be canceled, leaving me the limit as h approaches 0 of what I have left over, 10a plus 5h minus 1. At that point, I can finally allow h to become 0. And when I allow h to become 0, 5 times 0 just cancels out, and you're left with 10a minus 1. That's our derivative with respect to a. Final answer. For number 6 here, you have a radical function. F of x is equal to the square root of 2x minus 3. So I went in and I said, okay, in order to find the derivative, it's best to use the limit as x approaches a limit definition of a derivative. So f of x minus f of a over x minus a. In this case, f of x is just your function. Minus f of a is just your function with an a in the place of x, all divided by x minus a. In this type of problem, the goal is to eliminate the factor of x minus a in the numerator. I can't do that right now, so I'm thinking I need to algebraically manipulate and simplify the numerator. As soon as I see 2 square roots up there, you should be thinking of, well, multiply by the root conjugate, which is the exact two same square roots with the opposite sign in between. So I multiply by the root of 2x minus 3 plus the root of 2a minus 3. And I must do that in the numerator and the denominator. Now, from this step to the next, please keep in mind, all of this is still inside of a limit as x approaches a. My denominator is going to have the factor of x minus a times the sum of these square roots. And I haven't put any excess parentheses in this denominator. All of that's required. The group x minus a is multiplying that entire sum of these 2 square roots. So I'll leave that like it is. And I don't want to start distributing x minus a because I know the goal is that that factor of x minus a needs to be canceled. In my numerator, the whole point of multiplying by the conjugate is it ends up just to be the first term squared. If you square any square root, you just get what's inside. So I have the group 2x minus 3, and then it's always minus the last term squared, because you're going to have the negative square root of 2a minus 3 times the positive square root of 2a minus 3. That's going to give me minus the group 2a minus 3. And again, that group is mandatory. Now, I'm subtracting everything in this second group. And just like I said in the last problem, please remember, terms always cancel between f of a plus h and f of a, or between f of x and f of a here. Terms will never combine. So if you make a mistake like, ooh, -3 and -3, I'm going to put a -6. That cannot happen. That would be clear evidence that you're doing the problem wrong. They must cancel. So you say, okay, -3 minus a -3 does cancel. That tells me I did it right. And then what would you be left with? You'd be left with 2x minus 2a. Well, I can say, well, 2x minus 2a, I can factor a 2 out of that, and I'll have my x minus a, which is precisely what I wanted because I needed to cancel out that factor of x minus a in the denominator. So from this step to this step, all I did is I factored a 2 out of the only 2 remaining terms in the numerator. X minus a can now cancel with the denominator, and I'll get 2 divided by the sum of these 2 square roots, 2x minus 3 plus the root of 2a minus 3. And again, all of this is still inside of a limit as x approaches a. But now, since I've gotten rid of that factor of x minus a, there's no reason that we can't take the limit as x approaches a. So this tells us to allow x to become a. Everywhere you see an x, replace it with an a. So I have 2 over the root of 2a minus 3 plus the root of 2a minus 3. Those 2 roots would be the same. So you just say, well, 1 on the root of 2a minus 3 plus 1 on the root of 2a minus 3 is 2 on the root of 2a minus 3. And then I can say, well, now I have a factor of 2 in the numerator and denominator. I would want to cancel those out. So I can say my final glorious answer for this algebraic derivative would be 1 over the square root of 2a minus 3. Up next, for number 7, we're asked to find the algebraic derivative f prime of a using the limit definition of a derivative for 2 over x plus 7. So if I'm thinking about that, again, I would prefer myself to use the limit as x approaches a of f of x minus f of a over x minus a. And so then I can say, well, all right, again, f of x, that's just your function here, minus f of a, that's your function with an a in the place of x, divided by x minus a, all inside of a limit as x goes to a. Now, when I'm thinking, how do I simplify this expression? Well, automatically you should recognize it's a compound fraction. You don't want to have fractions inside of a fraction. So you multiply by every denominator you see on any fraction within the overall fraction. You say, oh, well, I'll multiply by x plus 7 and by a plus 7 then. And I have to multiply by an understood 1. So when I multiply the numerator by x plus 7 and a plus 7, I also multiply the denominator by x plus 7 and a plus 7. Now, from this to the next step, when I distribute that to each term in the numerator, the 2 is divided by x plus 7, so it's going to cancel out this multiplication of x plus 7, and I'll be left with 2 times a plus 7 for my first term. Then I'll have minus 2. The a plus 7s would cancel, but then that minus 2 is going to be multiplying the term that didn't cancel out with that fraction, and you'll have minus 2 times x plus 7. Your denominator, you need to be sure to show that you have 3 factors down there. You have the factor of x minus a, which now needs parentheses around it because it's being multiplied by the factor x plus 7 and a plus 7. Again, this is all still inside of a limit as x approaches a. My goal is to cancel out this factor of x minus a. When I'm looking at my numerator, I can see that, well, my constants, I'd have a plus 14 here and a minus 14 here. So just like we should always expect, hey, terms cancel out. It does. 14 minus 14, gone. Then I would be left with 2a minus 2x. I was thinking about that and said, well, I know I need a positive x minus a. So that 2a minus 2x that is left over, I want to factor a negative 2 out of that expression. If I do, then the x term would be positive and the a term would be negative. Please notice this would give you back precisely what we had. It would be positive 2a minus 2x, which is what you had in this step. But now this is in a format where it's more obvious, okay, I can cancel out that x minus a's now because it's a factor in the numerator and denominator. That leaves me the limit as x approaches a of what's remaining, negative 2 over x plus 7 times a plus 7. And when I take that limit as x approaches a, I would get negative 2 over a plus 7 times a plus 7, which is just better written as negative 2 over a plus 7 quantity squared. Okay, guys, I will start back with another video part 2 for the remaining problems.